So, good morning to everyone present here. Today, I, Simran, welcome all of you to another podcast of Ruburu series organized by R. Baba DAV College, Patala. And our guest of honor for today is Dr. Uday Mehta. He is currently working as a professor at Indian Institute of Sciences, Bangalore. He pursued his BSc from Presidency College, Calcutta, and MSc from IIT Kanpur. Then he shifted to Columbia University for MPhil and PhD. His postdoctorate stay was at University of California. Then he returned back to IIT Kanpur, and after a year he shifted to Indian Institute of Sciences, Bangalore. The major areas of his interest are hydrogels, metallohydrogels, organic inorganic hybrid compounds, photoluminescent sensors, etc. He, along with his team, have now developed a technique for low-cost paper-based photoluminescent sensors for enzymes in bio-related small molecules. He has been awarded many honors of national repute, including the SS Bhatnagar Award in Chemical Sciences in 2001. Sir, it's a great pleasure to have you with us today, and it's great to have you here. So, I would like to begin with a very basic question, sir. What all things basically inspired you to begin your journey in the field of chemistry?
Okay, so going back several decades, I grew up in a small steel township west of Kolkata. My father was an analytical chemist in the Durgapur steel plant. And, as kids, we would often have many questions. And my father was always very patient to answer the questions, particularly about nature. And since he was a chemist, there was a little bit of bias, I guess, in my asking questions which are relevant to chemistry. And when I was in high school, we had a slightly different system those days. It was 9th, 10th, and 11th. So the school leaving was after class 11. So at that time, you sort of specialize in science or humanities or commerce. So he brought me a book on inorganic chemistry, very old classical book. Nowadays, I think nobody would remember it, called Partington. So I literally read the book from cover to cover, and whatever was possible to do, some experiments which were possible to do in the kitchen during my mother's absence, I used to do that. So that kind of generated a very fond interest in chemistry from my early childhood, I would say.
So, sir, what all challenges and hurdles you faced during this journey, and maybe you're still facing them now?
I may have to think a little bit because certain things that I wanted to do during my, let's say, school days, they were not possible simply because it was, as I said, it was not a town where everything was available. If I had lived in a bigger town, in one of the metros, perhaps I could have done a little bit better in terms of learning on my own, listening to perhaps well-known chemists and other scientists, which was pretty much absent those days in towns which are non-metro towns. So I'm not the only one. I think those who grew up in non-metro towns, they all had a bit of handicap, I would say. So this was a bit of challenge, and after I finished high school, then subsequent to that, I was pretty much on my own. There were no pressure from anyone to pursue anything, other than what I was interested in. So I was able to pursue chemistry because that's what I was interested in, and I haven't had any significant difficulties, along the path.
Okay, sir, as we know, you have done a great work on photoluminescence. So, can you just give us an overview of that topic?
Okay, This is photoluminescence essentially indicates emission of light upon excitation with light. So fluorescent stickers that you often see on roads, many road signs are actually painted with fluorescent stickers, and they employ essentially the same principle, that you shine them with light and they emit light of a slightly different color. And in fact, a very simple experiment can be done. If you take a, let me see if I have one of these with me. If you take a highlighter, this is a red highlighter, but if you take a pink highlighter and put a laser beam here, the green laser here, so the green color will become yellow. So that's a very simple experiment to show photoluminescence. I don't have a green laser handy, otherwise I would have shown you with a pink highlighter. So that's an example of photoluminescence, where you shine light of one color and it emits light of a different color. It has many applications in science in general, in chemistry and biology in particular, for visualizing, for example, certain kinds of processes in cells. But our entry in, or our interest in photoluminescence started almost 12 years ago through a simple project that one of the undergraduate students in my group from Delhi University, so she was a summer intern. So she, along with another student, initiated a project. It was not planned the way it eventually evolved. You know, many scientific projects are actually they evolve because you start with a question, you ask a question, and you don't know the answer, and you don't know where it will take you to. And this particular project on photoluminescence, which we are pursuing for the last 12 years, and perhaps it will go on for some more, it really started like that. So basically the idea is to generate light through photo excitation. So photoluminescence, you excite with light and you generate photoluminescence.
So how does photo excitation actually works?
It works, for example, you can use sunlight in some cases, but sunlight is a mixture of lights of different color, as we know, vitriol. So sunlight is not a good way to photo excite, because if you have a molecule that absorbs light, then you need to shine it with light at which it absorbs. For example, something which is yellow in color will absorb blue light. So to make it excited to its photochemically excited state, you need to excite with blue light. Similarly, if something appears, let's say, yellow, it will absorb something that emits yellow, it will absorb more in the pink range. So you have to, in a greenish range. So you have to excite with light which is of the right wavelength. And lasers come in very handy because green laser has a wavelength of 530 approximately nanometers. So that can be used for demonstrating. I'm talking about simple demonstration to people who are not familiar with photoluminescence. So you basically use light of a certain wavelength, and typically it is done in spectrometers, where light from 200 to 700 nanometers can be generated with a very narrow range of wavelengths.
So how does that work on an atomic level?
Okay, we are not talking about atoms. We are talking about, of course, the luminescence identification of atoms. They all came from study with atomic spectra, but we deal with molecules. So molecules have different groups of electrons, as we know from bonding. And typically what happens is that there is a certain energy difference between what is called a ground state and a first excited state, where you take an electron from the highest occupied molecular orbital and give it exactly the amount of energy it requires to go to the lowest unoccupied molecular orbital. So as I'm showing with my two hands, my left hand is the lower energy level, right hand is the upper but vacant energy level. So you pump an electron from the lower one to the upper one by providing the difference in the energy. And that difference in the energy comes from a light of the correct wavelength. So if you shine a molecule which has this much of energy level difference, and if you supply exactly the same energy, but give and take a few kilocalories sometimes, then the electron in the lower state will get excited to the upper state. And that's how you generate a photoexcited state. And then when the electron decides to come back to the ground state, it would normally emit. It can happen in many ways, but if it happens to what is called a radiative transition, that is, it emits light of a certain wavelength, then you will see a flash of light. So that's how photoluminescence works. First you excite, and then you see the emission.
So does it has anything to do with the photons?
Of course, it has to do with photons because you are exciting with a photon, and if you see luminescence, that is also a photon that is coming out of the excited state.
Okay, sir. So, what according to you has been the biggest achievement of yours till now?
Okay, I don't think that I can really single out anything as a biggest achievement because I have worked here for the last almost 30 years, 30 plus years, and there have been many small achievements, many small experiments, and when you put them together and give it a try to look at things with a broader perspective. Okay, that gives me the most satisfaction because of course the work that we are doing on chemiluminescence, it has some practical applications, and we are already working on a few possibilities of detecting small amounts of certain analytes which may be of practical interest, but detecting certain kinds of abnormalities in the blood profile, let us say. And we are also trying to develop a small handheld equipment which may help in this diagnosis. So if we are able to take it to practical application, I think that would be the most satisfying thing in my life.
So, sir, I would like to be a bit more personal. When you received that award, SS Bhatnagar Award in 2001, so what was the feeling at the time?
Well, it was good to know that the work that we had done. This was 2001. It was good to know that the community, the scientific community in the country in general, and the chemistry community in particular, recognized the work and the hard work that my students put in. Because I don't do any lab work myself. Everything is done by the students. So it was, I would say, a recognition of the hard work and the intellectual quality of my students that they put in into the work.
Okay, sir. So, sir, other than the photoluminescence, what are your other areas of interest in chemistry?
Yeah. In terms of research, because I have some interest outside research also, and that connects to education, and that I will highlight also. Other than photoluminescence, see, photoluminescence is just a technique, but we use it for a variety of applications. So I will not elaborate on these details, but in the early days, we also looked at for example, how to make one mirror image form of the molecule in preference to the other image, in mirror image form. In other words, as you know that our hands, two hands for example, are mirror images of each other, but they are not superimposed. Okay. So molecules which have such a property are called chiral molecules or optically active molecules. For example, sugar, amino acids, and so on. So in the early part of my career, some of our interest was to make one and not the other mirror image form. So that's how we started. And subsequently, we have also worked on materials which look like gels or jellies. For instance, all of you are familiar with various kinds of cosmetics like toothpaste, hair gels, which are neither solid nor liquids, right? So they flow like a liquid, but they stay like a solid. So these are called gels. Similarly, in food industry also you have a lot of materials, a lot of food products are like jellies or gels. So we accidentally discovered almost 20 plus years ago a particular molecular system. When you combine two of them, it leads to the formation of a gel. And it was not very well known at that time, this kind of system. So we spent quite a bit of time from almost 2000 to 2012, 15, looking at the properties of these gels and for their potential applications. And I should also point out that the work that we have been doing with photoluminescence also involve gels of a particular kind. Somewhat specialized gels involving a group of metals which are collectively called lantanides, or also known as rare earths. So these are some of our other areas of scientific activities, but I'm also interested in a lot of outreach programs in education. So I participate and I organize a variety of outreach programs at all levels, from high school to the undergraduate level and to the postgraduate.
Okay, sir. So generally there is a taboo that people from science department are considered as a bookworm. So can you clarify them as like we do things other than studies too, like your
Yeah,
other hobbies and interests?
I don't think that I don't think that you can single out science, because I would say that more than science, the people who study humanities, they probably read a lot more, because we do experiments, we do things in the laboratory, so that kind of complements the reading that we do. But then there's so much of scientific literature that is available nowadays, and there has really been an explosion in the number of scientific papers which are published in hundreds, if not thousands, of journals. So it does take some time to sit down and read those. Even those which are relevant to my own research, I don't think I have time. 24 hours is enough for me to even get a glimpse of what has been published today. So yeah, I would not say that only science students or professors are bookworms. Those who love to read, they will always read. But in any career, you have to give enough time to do the background reading. Because what we would like to do tomorrow would really depend upon what others have done today, others than we have done today. So that requires quite a bit of background work, reading, and it's 2022, so it is very hard to do something very original, and you need to do enough literature work and make sure that what you are proposing to do tomorrow has not already been done by others, and that of course would require a lot of reading, searching, and all that. Maybe 15 years ago it was difficult, but nowadays various search engines. Google is only one of them, but for scientific research, we rely on other types of more specific search engines. They help a lot because you don't necessarily have to go to the library and spend hours searching for old work. Everything is at the click of a mouse, so to speak.
Okay. So can you elaborate us about your stay at Columbia?
Okay, I think that was, I stayed in Colombia for about a little over 4 years. And I would say that was probably the best time that in my scientific career. Because, well, initial first semester was a bit of a challenge, because, you go from one country to another and you see a lot of bright students, very, very bright students. In my class, there were about 22 students covering all areas of chemistry. A small number were international students, Mostly they were Americans. And ultimately, in the first semester, we had to do 4 coursework. We have to take 4 courses. And the courses were not difficult at all because, I studied in 2 reputed institutions for my undergraduate and master's. And I had excellent teachers in both places. So they really trained me well. So I had no difficulty with the coursework at Columbia. I think the work needed a little bit more push, a little more hard work compared to what I was used to, but that was not a problem. I also enjoyed, I joined the research group probably in October. I started in August. In October of the year I joined. And my research group had again extremely talented students, and it was really a pleasure interacting with them. So and my supervisor, Professor Ronald Breslow, is no more, and he had one of the sharpest minds. So, interacting with my advisor and my other colleagues, both in my class and those who are either above or before me in the graduate school, it was really fantastic. I think at that time, Columbia chemistry, particularly organic chemistry, had really world-class faculty. I mean, even now they have, but at that time, they were very, very famous. Each of the 6 was famous in his own respective area, and it was really wonderful experience.
So, did you find any difference between education system here in India and that of Colombia?
That's a loaded question. Yes, in fact, this would bring me back to the kind of system that we have over many years, because we generally teach our students to answer questions. Okay. And I often jokingly say that nowadays those who go to coaching school are only taught how to find 3 wrong answers, and sometimes not even worry about the correct answer, because by choice, by elimination, it gets settled. Jokes apart, we do not often encourage students to ask questions, try to be creative. And that is one striking difference that I observed in the US, that in US, people are encouraged to ask questions, try to be creative, come up with their own thoughts, own ideas. And that was one of the biggest differences that I found between our system and their system.
So, over the years, how the education system has changed in India, according to you?
Can you repeat?
Over the years, past few years, how the education system in India has changed?
Okay, I think we have had some changes in the way it is taught, because the use of computers and other media clearly has made a difference in the last 10 plus years. I'm not talking about the first 10 years of this century, because things were not very readily available. Network was still expensive, access to network. But in the last 10 years, there has been a revolution in the way you can access teaching material, and in the way you can convey things. And during the last 2 years of the pandemic, the use of remote learning processes, it was always there, but we really made use of the internet and high technology to make sure that we don't lose out in teaching and in learning. And of course, there have been many difficulties of accessibility, but that will always be there whenever you try to adopt a new system. But I think, in a sense, the last 2 years have also taught us that there are more ways to teach than the classical classroom teaching. I don't think classroom teaching can be replaced by anything else. I would still, I may sound old-fashioned, but I think that is still the best way to teach and to learn, because that brings the in other words, in-person teaching. In terms of subjects and curriculum, yes, there have been changes, but then the changes have, in my opinion, have been incremental. We haven't had a major, I would say, the working out of the way teaching needs to be done, the course contents, the examination system. I believe that the new education policy, when implemented, will make some major changes, but that is yet to be seen.
Sir, I saw your FB account and there were many posts related to nature and flowers. So, do you get any inspiration from this nature in the field of chemistry?
Pardon me, say that again.
On your FB account, we have seen many posts related to nature and flowers.
Yes.
So, do you get any inspiration in the field of chemistry from this nature?
Oh yeah, absolutely. I particularly in the last 2 years, when I used to live in the campus. I was in campus, and during the lockdown, campus was the only thing that we could connect us to. Because the students were not around, most people were not allowed to come or go. So we ended up exploring the campus a lot, and that's how we see a lot of nature there. But ultimately, we divide science according to our convenience: physics, chemistry, mathematics, biology, and many others. Within chemistry, we divide it again according to certain classifications: organic, inorganic, physical. But ultimately, regardless of what your narrow area of interest is, you're still trying to understand part of nature. So ultimately, it is nature that inspires us to ask questions and to find answers. And as a result, anything that I see in nature excites me, interests me. And yes, sometimes it does make me ask questions. And sometimes the question may be in chemistry, sometimes it may not be in chemistry. But yes, nature should inspire everyone to ask questions, and then depending upon his or her interest, it can be relevant to physics or chemistry or biology or even mathematics. So sometimes you see certain flowers in a very perfect geometrical shape. Like yesterday, I was exploring one, which you will also find on my Facebook page. It's called. It's a flower native of Argentina and Brazil. It's in our campus. There's the 5 very, very symmetric petals. And there are many such flowers. So then I do know a colleague who has actually worked on shapes of the flowers, petals, and so on. So yes, nature does give inspiration to ask questions, and in all areas of science, if not beyond, art also.
So, what do you think there are major links between bio and chemistry?
Link between?
Between biology and chemistry.
Okay, I think biology to a large extent is in fact chemistry. Because if you look at the size, if you look at the size of the objects which, let's say, physics handles very, very small particles and very, very large objects like the planets, right? Chemists are somewhere on the lower side. They look at molecules and aggregates of molecules, whereas biology deals with much larger molecules. The difference is that in biology, everything happens within, let's say, a biological system. And chemists don't have those constraints. For example, at least in mammals, every reaction that has to happen for me to survive and to speak here happens at 37 degrees and in water. On the other hand, chemists don't have those constraints. They can use any temperature they want, from minus 150 to plus 1000 or more degrees, any solvents of choice. But then there's a connection. The processes that are taking place in our body, which is governed by, the biology, are all chemical reactions, except that they're happening in a different environment and in a much more complex environment. So biology, I would say, is some complex manifestation of chemistry. If I have to, connect chemistry and biology from the chemistry side, that's how I will describe biology. And of course, the additional thing is that it happens in a living system. But in chemistry, there is nothing. There is a living system. I hope that answers your question.
Yes, sir. Sir, there was a post in your FB account that said chemistry is fun.
Yes.
But many of the students, even many of my classmates, find it a very difficult subject. And they just see it as a mere cramming of the reactions. According to them, organic chemistry is just cramming of reactions. So, can you tell us more ways how to make chemistry fun?
Yeah, this is actually a lecture demonstration that I do as part of my outreach programs. The nearest place where I have done with respect to your location is in HMB in Jalandhar. And this was a part of a DSP inspired camp. So for a long time, I have looked at, for example, the CBSE syllabus in chemistry. And I think all the subjects will have very similar issues. But in chemistry, it's very descriptive. And whether it is CBSE or State Board or ICSE, I think there is not much of a difference in terms of the overall organization. But I often feel that so much of specialization is not required at 11th and 12th, because you also learn physics, you also learn biology and mathematics. So the importance of chemistry in daily life, you will see if you look at the CBSE syllabus, there's a chapter called Chemistry in Everyday Life, and that's the last chapter in your class 12 textbook. In my opinion, that should be the first chapter in class 11. And that's how people should be made interested in chemistry. Since morning, the time you squeeze out the toothpaste on your toothbrush, you are seeing you are enjoying the benefits of chemistry. But I think connecting chemistry to everyday life is something that needs to be done, and that will make chemistry much more fun. And in the 2-hour show that I often do, this is what I try to bring out, that chemistry is not just a collection of reactions. I mean, that is something you study when you become super specialized. But you have to look at a bigger picture of what chemistry does for us in everyday life. And that big picture is often missing at the high school level. That's why students, understandably, think that chemistry is just memorization of a bunch of reactions and nothing more than that. On the other hand, chemistry is also considered to be the central, creative, and useful subject. Chemistry is the only subject only branch of science where you create molecules and materials. Nobody else can do it. Except in biology, it happens on its own, right? But you and I don't know if you're a chemistry student, I assume you're a chemistry student. You and I can make molecules, we can make new materials with new products, which others can study, others can engineer to make commercial products. But as they say, the fundamental way to make molecules of the creative aspect, that's the chemistry. That's why chemistry is called a central subject.
Okay, sir. So if you don't mind, would you like to tell us about your family life? About your family life.
About my family? Okay. As I mentioned earlier, that my father was a chemist. He was working in a steel plant, and I have an elder sister who is not a chemist, and a younger brother who is a chemist. Of course, our specialization happened much later. So in my childhood, which was in geography in West Bengal, we really had a lot of fun doing experiments, asking questions, and my mother was not working. She was always very supportive of our studies. So, and going back to the 1960s and 70s when we were in schools, um, opportunities were very limited. So, like nowadays, you can graduate from high school and do many possibilities. There are many career possibilities, but for us, it was very limited. But we always had very strong support of our parents. And then when I went to school, went to college in Presidency College in Kolkata, and then I Kanpur. Again, the family support was very, very strong. My family at that time relocated to Kolkata because my father passed away. And that did create some difficulties, but my family really supported me in pursuing higher studies. And I must acknowledge that their support, particularly my mother, my elder sister, my younger brother too. And I came back to India, and the support, of course, continued. It turns out that my wife also has a chemistry background, but she's a chemical engineer. And we support each other's work because both of us are working. I think that kind of sums up my family.
Yes,
I
sir.
have one son. He's a mathematician. He's doing PhD in mathematics. About halfway.
Yes, sir. So every successful man has a great teacher behind him. So, is there any such kind of person behind you?
Many. Not one teacher, but many teachers. Um, and my first, foremost, I must mention my father. He was one of the best teachers I had, and he was very friendly to me when I went to school and then to college. Then in college, I had several teachers in Presidency College in chemistry, in all areas of chemistry. In particular, I will mention Professor P.K. Sen. He really taught us organic chemistry from a different perspective. And when I went to IIT Kanpur, I had again many great teachers, Professor Chandrasekharan, Professor S. Ranganathan, to name a few. They both taught really, really well organic chemistry. Then I had another teacher, Professor P.T. Simon. She taught physical chemistry, spectroscopy really, really well. And subsequently, when I went to Columbia, my supervisor, Professor Ronald Breslow, and there were other teachers, Professor Gilbert Storr, Professor Koji Nakanishi, they were also great teachers. So I learned not from one, but from many, many great teachers. And I must consider myself very, very fortunate that I was in contact with so many great teachers during my scientific career. And I keep learning from my younger colleagues who are also great teachers, and some of them are excellent.
Okay, so my last question for you is, can you provide us with some guidelines for the youth which is interested more in internet, social media and technology rather than the practical things?
Yeah, I think whatever one wants to do, one has to work hard. Now, I also see among my research students, and I hear it from my other colleagues also, that internet is meant to be a problem solver, in fact, because you find many things that otherwise would have been extremely difficult to find, 10, 15 years ago. But unless you use it properly, use it more and misuse it less, you will end up spending more time. So I think a lot of our students at all ages end up using non-productive hours with internet, and I think that should be minimized. But other than that, everyone should pursue whatever he or she is interested in, and hopefully, you know, I believe that every individual can be creative, provided he or she finds, hopefully quickly, where the interest lies. If we try to force somebody who is a good painter to do, high energy physics research, it will not lead you anywhere. Both the student and the teacher will get frustrated. So I think there are many opportunities now. And the students should be encouraged to do whatever, wherever their expertise or wherever their interest lies and wherever they can be creative. This is also something I must say that, I have seen at least in the US, this is something that happens rather universal, that eventually, no matter where you come from, you always find your uh, the kind of work where your expertise, your interest um, would be satisfied. And for example, I often say that since I'm a pianist, that I'm actually pursuing my hobby and getting paid for it. So everybody should think similarly about their own work. That it's something that I enjoy doing. So in a sense, it's my hobby. I'm only pursuing it, and I get paid for it. So there is nothing better than that. And if the majority of the people think along in a similar way, then I think many of our problems will be solved.
Thank you so much, sir, for sharing your valuable and honored thoughts with us. It
Thank
was
you very
great
much.
having you here today. And at last,
Thank
I would like to thank our principal, Dr. Ekta Khosla, for organizing such a great event. And I would also like to thank the convener of this show, Mrs. Ekta Bhandari, and the overall in charge, Mrs. Lucky Sharma. Thank you,
Thank you
everyone.
very much. Bye bye. Shall I log off?
Yes, sir.
Thank you. Thank you all. Bye bye.
Thank you so much, sir.